I welcome you all to the Spark Research YouTube channel. This is Dr. Vichandra, Assistant Professor in the Department of ECE. And here is another session for this particular course, Signal Processing. And this is the first part of the unit third. Here we are going to talk about the analysis of discrete time signals and system. Particularly, we will take the contents from these topics, right? First, we will talk about the discrete time transform. Then we will talk about the IDFT, inverse discrete Fourier transform. Then we will see fast Fourier transform, that is FFT, and we will also see the distribution in time frequency transform, that is DIT FFT, and distribution in the frequency, that is fast Fourier transform, that is DIF FFT. Okay, so let's go ahead. Here is the syllabus, and in this session we are going to take this, right? So particularly we will focus on the DFT and IDFT. Okay, so first question is that what do you mean by this DFT? So the DFT of a sequence action, and what is this sequence action, right? Means any type of signals, like at a particular action you have the amplitude, right, 1, then some amplitude 2, 4, at like at the regular time interval you have the any samples values, right? So that is called the sequence action of length n. Length n may be like 2, like here it is 4, length n is equal to 4, so 6, 8, or any numbers, right? So for that, if you want to find out, this is in the, suppose in the time domain, and time domain means we are representing in n domain, right? So if you want to convert this time domain into the frequency, so we are calling it as a x of k. Then how will you convert this time domain sequence in the frequency domain? So the formula is summation of n equal to 0 to capital N minus 1, and then x of n. This x of n is your this sequence, right? And multiply it exponential of minus j twice pi by n kn, right? So we have to multiply by this exponential function in order to convert the xn into the x of k, right? So it will convert our time domain sequence into the frequency domain sequence, right? So this is called the DFT, that is discrete Fourier transform. Why this is discrete? Discrete because the samples are discretized. And why Fourier? Fourier transform we are doing. If you remember in analog one, the instead of the discrete continuous Fourier transform, we have used the x of t and exponential of minus j omega t, right? And similarly, if you want to convert back, that is x of k into the x of n, then use this expression, that is 1 by n summation of k is equal to 0 to n minus 1, and x of k is this one, right? So this is your x of k, and e to the power j twice pi by capital N k of n, right? So xn is the reconstructed message. So here is the overall. So DFT, you can see this equation same only. I have rewritten it so that you will get it in a better manner. So here x of n e to the power minus j twice pi k divided by n. A small n is the number of the sequence, right? So here this is the one, right? So suppose this is the one, this is two, this is three, and this is four. So n will be very small, n will be one for this one, two, three, like, and capital N is here. Capital N is always constant, that is equal to, here it is capital N is equal to 4, right? So similarly here you can find out the x of n, that is convert back. Okay, so here is an example. Suppose a finite duration sequence of length L is given as x of n is equal to 1. And when will it be 1? So in between 0 to L minus 1, otherwise it is 0. So determine the endpoint DFT of this sequence. This is your sequence. So we have to find out the DFT of this. So as you know, we have the formula x of n e to the power minus j omega n, and then n is equal to 0 to L minus 1. So put it, and since this is 1, So here xn is equal to 1. So 1 into and then formula e to the power minus j omega n. And now here what will happen? So 1 minus of e to the power minus j omega n divided by 1 minus j omega, right? So if we'll add, then you will get this final value. And how will you get this final value? So this is nothing. If you will put it, then you will get something like geometrical progression, that is gp ar square and like that. Okay, so what will be the addition? The addition, if r is less than equal to 1 as it is here, so as infinity it equal to a divided by 1 minus r, right? So if you put all these values, you will get. Okay, so here now, so in the DFT, we have learned that how to find the DFT for a sequence and IDFT, that is inverse Fourier transform for the same, right? So we have already now here we have to find the generalized the DFT as a linear transformation. So here xk will be again the same things. Here what is the measure objective? Instead of the using e to the power minus j twice pi k n divided by n, our target is to replace it by w of n k n, right? So w of n, this capital N is the here this capital N, so these both are same only. And the k of n, so k of n is the here a small one, right? So the both w and k and this e to the power minus j pi n divided by n both are same only, right? And why are we doing? Because if you will see, an action is varying, action is input, right? Action is input, like suppose these are the sequence 1 2 3 4, these are the sequence for action. Like for this amplitude it's suppose 1, here it is suppose 1, here also suppose 1, and here also 1, then amplitudes are 1, or suppose any variable, suppose 1 2 1, any variable for action, but these are the fixed values. So why to calculate always this? In order to find the value of xk, so that is why we are replacing it w and k. So what will be the value of wn? Wn is nothing. This is the most important results that you must have to remember. So wn is equal to e to the power minus j twice pi divided by capital N. And the remaining here k and n are remaining now, so we will put it here, right? So always remember, this is the one of the important results. Okay. And now how we'll solve? So xn is x, that you can get the value of xn, like x0 x1 whatever the inputs. So this is the sequence, so xn you will get it. And then wn you can write the 1 and the wn actually wn 0, then wn the 1, wn2, then wn3, and like that. So you can rewrite this, and whenever you want you can make it generalized one. So this is the generalized one, right? So here is an example. Suppose compute the DFT of 4-point sequence, right? So here 4.0 1 and then 2 amplitude and then 3 for this sequence, right? So here suppose the 0 amplitude is there, 1 amplitude, and here amplitude is 2, and here the amplitude is 3, right? So in this case, Wn we will find out. So W capital N is how much? 4. Capital N is how much? 4. Why is it 4? Because total how many sequence are there? 4 sequence, right? So in order to get the W, 4 matrix, w40 w4 the all zeros, w40, then w41, then w42, then w43, and so again 00, then 2 and 3, and then the 4, and then 3 again. So this will be both, so both will be same. And all these here this term, actually this term here the w0 w0, here w0 w0, and then here w41, and then the last, and this one same, and here the last and this one same, and the b this one will be same. Here similarly this one and this one will be same. So now you can calculate these values. So if you calculate w and 0, and like how will you calculate? So w and 0 nothing, e to the power j twice pi, and then and then k, then you can get the value w and these values 1 1 minus 1, like that. Further, if you will put all these, like multiply this matrix, this into this 0, 1, 2, 3, you will get this final result, right? So how will you get this? So n is for n is equal to 4 here, and wn is what? E to the power minus j twice pi by n. So put the value, like for w4, as for example, e to the power minus j twice pi by 4, right? So put the values, e to the power minus j and then pi by 2. So e to the power minus j twice pi by 2 is nothing, that is your minus j. Okay, like e to the minus theta is equal to, you can write cos theta plus minus sine j sine theta. So cos theta is nothing here, pi by 2, that is cos theta is 0, and sine theta will be minus 1. So this will be minus of j, right? So here is the final value. So w40 is equal to 1, w41 is equal to minus 1, w42 is equal to minus 1, and w43 is equal to minus 1, right? So how we'll get all these values? So put here the values of the n, right? So a small capital, like a small n, that is 1. So here, into 1 into 2 into, like here you can put. So you can put the values and you can get. Again, these are the very important results you should remember. Okay, so here are the some DFT properties. So xn is xk, the linearity property, it will follow, periodicity follow, then time shift, it will shift in the time domain. Then here you can see the multiplication of xk with the omega, the w, and then km, right? Frequency you can shift, then circular convolution in the lane in the time domain means x of nk, it will be product in the frequency domain. Similarly, in the multiplication conjugation properties, you can check. Here IDFT properties, almost all are similar, you can check it. Circular convolution. So let's take an example of the circular convolution. Suppose x1 is here and x2, two different sequence are there, right? So how will you find the DFT for this? So that is called a circular convolution. So here suppose x1 is there, 1, 2 and 3, and x1 is 4, 5, 6. So how will you do? So like suppose 4, 5 and 6. So we will multiply, like first we will find the y0, y1, y2, right? So how we'll do? So x of k and x2 and minus k, right? So this will multiply with this, and again this will multiply with this, and third will multiply with the first one, right? So y0 first, x1 0, y2 x2 0, that is this is the x1 0 and this is your x2 3, x2 0, then x1 and x2 2, and then x1 2 and x1 1. So that is y0. Once you will get the y0, similarly you can get the value of y1 here, x1 0 and x2 1 and x1 1 and x2 0 and x2 and x, right? So you can get the values, and finally you will get the value of the circular convolution. Now, what is the fast Fourier transform? So fast Fourier transform is an efficient algorithm used to compute the discrete Fourier transform of a sequence quickly. So this is the important word, quickly, right? So you can do the DFT, but problem is that it will take lots of time. So how can we reduce? So using the FFT, fast Fourier transform. So normally instead of computing DFT for n point sequence requires n square multiplication, right? So here we'll reduce the complexity and we'll perform for some step only, right? So there are two techniques. One is called decimation in time, DIT, and one is called decimation in frequency, that is DIF. This is just for representation only, that is whenever questions will come related to the DFFT, fast Fourier transform, remember we have to draw the some butterfly type of structure. This is called butterfly type of structure, right? So always remember. So butterfly type of structure means FFT, right? And there are two types. One is 8, 4 and 2, and one is 2, 4, 8. So and again this is depending on the DIT FFT, right? Okay, let's see. So method of decimation in the frequency, right? So here we are, the converting, we are getting the values of x of k, that is Fourier transform here only, discrete Fourier transform only. So here decimation in frequency only. So in the left side you can see here total total inputs, suppose 8, so 8 inputs, then here butterfly structure, here 2 is a 4 and 4, right? So again 8, and then here 4, two types of the butterfly, two inputs, two outputs, 2 2, again 2, and then 2, right? So 8, 4 and 2, so 8 cross 1, 4 cross 2, and 2 cross 4, so total 8 8 8. So this is the block diagram related to your decimation in frequency, and just reverse in the decimation in time. So in decimation in time, we will see initially it will convert 2 cross 4, then 4, and then 8, right? So we'll continue to see. And how is it working? So block diagram for the inverse, right? So this is for the block diagram for the DFT, and this is for the IDFT, not IDFT, this is IFFT, inverse Fourier fast Fourier transform, right? So here you can see that whatever like we are multiplying, the same values here you will get it, right? So let's see how to convert some example. Here is the example. Suppose the sequence is 0 DFT sequence xk for 0 0 in between 0 to 3, and evaluate the DFT using the decimation in frequency, that is FFT method. Okay. One interesting concept is there, that is called the bit reversal. So I will briefly discuss about how to solve this FFT, like for decimation in time and decimation in frequency in another special session, that is it will be dedicated to only DFT and FFT, because this is the very important topic. DIT, like FF, fast Fourier transform, right? How to find out the fast Fourier transform using both methods. So I will talk about it very briefly. So here just I'm going quickly because session will be very longer, right? So here first multiply, like here minus 1, and here upper side if you are going, no need to multiply, put the input values in the left side and multiply, and add it here, right? So like here 8, and then here if you are multiplying and then getting 4, then 8 plus 4, that is 12, and like that you can keep on multiplying and you will get the values of x0, x2, x1, and x4. Why this bit reversal, I will again discuss it briefly in the next session. Similarly here, like how to solve another question, FFT only. So here is your inputs, this is your for evaluate the DFT using the decimation in frequency FFT method, right? So put the values of input, multiply and add, you will get the values. And here number of the complex, how many? So n by 2, n is the total number of sequence, and log of 2n, so you will get the value of the number of steps. Okay. So now another method is the decimation in frequency. So here again decimation in frequency, like how will you get? So we'll decimate in the frequency here, like x of 2m and then omega n 2 of 2mk. And as for and then finally you will get the x of k, the addition of this odd and even part, right? So here how will you do? So again, if you remember in the decimation and frequency, we have done like 8, 4 and 2. Here just reverse. So here we have the, initially we are using 2 butterfly structure. So total 2 cross 2, that is total 2, total 4, that is 2, 8, 4 butterfly structures. Here we are using 4 cross 4 butterfly structures. So again 2 cross 2 butterfly structure, this is called 1 cross 1 only. So again, and like that, this is the 8 4 cross 4, so here total 8 like a structure. So here if you see 4 2 and 1 butterfly structure, right? So just reverse to the decimation in the frequency. This is for the fast Fourier transform, and this is for the inverse Fourier transform, right? So let's see the example here. Just for example, now here we have to find out the DFT using the decimation in the time, right? So put the values, input values, and here actually decimation in time. First we will multiply dn0, right? And if you saw that in the decimation in the frequency, now we are multiplying later. So that is the difference while solving. Okay, so we'll take the examples and discuss briefly in the another session. I will drop the link in the description section. You may also go through that. The other things are almost same, right? So you are just going to multiply and then add, and then you will get the final values. Same process here again. This is the another one example for this. So find the its inverse DFT using the decimation in time FFT. Okay, thank you to join the sessions, and we'll shortly come with the another sessions. Thank you.